Okay, welcome back. This is a third part for we'll call it a series on confidence intervals for the population proportion. So to pick it back up, we are going to construct our confidence interval using a point estimate, so a value of p hat plus or minus the margin of error. This margin of error is calculated by taking a critical value, z of alpha over 2, times the standard error, which is p hat 1 minus p hat all over n. Okay, so first of all, this construction is based on the fact that p hat is normally distributed, centered at p with a standard deviation of square root p 1 minus p all over n. Now, in order for this to be true, you may recall that there are a couple things that we need to check. First of all, I need to make sure that my n times p times 1 minus p is at least 10. So in the world of confidence intervals, I'm going to have to use p hat here. So I still want to verify that this requirement is met. And the second requirement is that our sample size is no more than 5% of our population. So keep in mind that when you're doing confidence intervals, you'll want to check these. Now, if you have a really large population, for instance, like the whole United States, where you have millions of people, likelihood the second condition is not going to be a problem. But you do want to check these first to make sure that this strategy is appropriate. All right, so I want to talk about the effects of choosing different confidence levels. So let's see, where was that? Previously, I showed you how you could find these different critical values that correspond to different confidence intervals. So I want you to notice that as our confidence levels go up, from 90 to 95 to 98 to 99, these critical values are going up. That's because we're taking wider and wider, we're creating wider and wider intervals, so we're going further and further out in the standard normal distribution. So you'll notice that as the confidence goes up, your margin of error is going to get bigger. That's if you're holding everything else constant. Now, I would say this, let's just say that you were going to make a wager about the outcome of an election, and your guess was that 52% would be, in favor of a certain candidate, and you were going to be betting, $1,000. Now, in order to win, in this case, the outcome would have to be exactly 52%. Probably not many people would be willing to wager $1,000 if they had to guess exactly what the percentage was going to be. But if you gave yourself a little bit of wiggle room, so maybe let's just talk about some percentage points, that the person was going to capture 52% of the vote, but you said plus or minus 2%. So it could be somewhere between 50 and 54. You might be a little bit more willing to take that wager. If you said it was 52% plus or minus 10%, a lot more people would probably be willing to take the bet. And as I keep giving myself more and more wiggle room, so maybe if I go up to 25%, so your confidence can go up when this corresponds to the margin of error. So as when you have greater confidence, you're going to end up with a larger margin of error. Those things rise and fall together. And you'll notice that has to do with the fact that the confidence level, this is determined by C. Okay, so that's one thing to keep in mind. Now, there's another element of this that's within our control, and that is the sample size. And so I want to think about what happens, as the sample size goes up or the sample size goes down, everything else held constant. So when your sample size goes up, your estimates are going to be more and more accurate. You're going to need less wiggle room to maintain the same confidence. Now, notice, if your sample size goes up, that means this denominator gets bigger, which would mean this whole quotient gets smaller, and so this then square root would be smaller, and your whole margin of error gets smaller. And when your sample size goes down, you're going to end up with a bigger margin of error. So I would encourage you to play around with some different values. So maybe make a table where you have different confidence levels, like 90%, 95%, and 99%. And then look at different sample sizes, so maybe n equals 100, n equals 1,000, and maybe n equals 10,000. And look at the different margins of error under some circumstances. Like for instance, earlier we said x equals 515 in a sample of 1,000, and with 95% confidence. And I think we ended up with a margin of error of like 3%. So you might see what changing some of these other things will do. Actually, let me just do one of these. Let's look at what happens when we change this to 99%. So clear, I'm going to go to my stat menu, scroll over to test, option A, and the only thing I'm going to change here is this to 99, and calculate. And so I need to take 0.55571 minus 0.515, and so now it's more like 4%. That's the margin of error. So notice again, the confidence is larger. My margin of error is larger. Now, what happens if I kept this the same, but and took a smaller sample size? So I'll go stat, test. So this time I'm going to change this to the x value to 51.5 out of 100. So I want to keep the same percentage, and I'll change this to 95. I think the problem there is I put a decimal in stat test. I'm going to go the other way, and let's calculate this one here. So 1 proportion z, 5150 out of 10,000, and now I have 0.5248, 0.5248 minus 0.515, and so now I get about a 1% margin of error. So I made my sample size a lot bigger, and that brought down the margin of error to just 1%. So that leads me to kind of the last topic for confidence intervals for proportions. Let's say that you have a goal of a certain confidence interval and maybe 98%, and a margin of error maybe 2%. And so you want to make sure you meet these standards. So this would be when you are planning to conduct a study. Then you might ask yourself, well, what sample size do I need in order to meet these goals? So there's a formula for this. N equals P, 1 minus P, Z of alpha over 2 all over E, quantity squared. Now, remember that this is in the planning stages. You're going to take a sample in order to estimate a population proportion. Well, once again, I see P's here. That's what I'm trying to estimate, so I'm going to have to use P hat. But wait a second, I haven't even done this yet. So the values that you're going to use for P hat, I'm going to say here, where P hat is a prior estimate. Now, if you don't have a prior estimate, I'm going to say otherwise use 0.5 and just assume that it's a 54 and 50 against type of situation. So let's do an example where we want to meet this confidence level of 98%, a margin of error of 2%, and I don't have a prior estimate. And so to get the minimum sample size, I would take 0.5, 1 minus 0.5, which is also 0.5. So this is always going to be then 0.25. Okay. And now The critical value that I want to use when for 98% confidence is 2.33. We found that out in a previous work. And my margin of error is 2%. Make sure you convert this to a decimal, 0.02, and then we'll square that. So let's see, I need to take 2.33 divided by 0.02, square that, and then multiply by 0.25. And I end up with 3393.0625. Now, always, I can't emphasize this enough, round up. So you're going to use 3394 in this situation for your minimum sample size. All right, that concludes this set of videos on calculating the a confidence interval for the sample for the population proportion. All right, bye.